Hello, welcome to today's webcast. My name is Brianne, and I will be your event specialist today. Following the presentation, we'll have a question and answer session. However, you can ask your question at any time during the presentation. Click the Ask a Question button, type your question in the open area, and click Ask Question to submit. We'll answer as many questions as time allows. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. If you are disconnected from the webcast, you can log on again using the login instructions provided to you. If you cannot log back on with these instructions, please call support at 866-271-7592. It is now my pleasure to turn the webcast over to your speaker, Ben Castor. Ben, the floor is yours.
Hi, thank you. My name is Ben Gaster, and I'm an architect at AMD, and I, in particular, over the last few years, I've been working on GPU computing, which is mainly focused to date on the GPU in particular, but as we go into the heterogeneous kind of era that AMD is bringing out with its fusion parts and other things, I've been looking more at the CPU again as well. Last week I gave a kind of introduction, high-level kind of bird's-eye view of heterogeneous computing and what that means with respect to AMD and its fusion parts, and kind of what the programming models kind of need to adapt to. And kind of one element of that programming model is OpenCL, and the rest of this webinar series is going to really specialize on that. And today I'm going to give a kind of quite quick and high-level overview of OpenCL, and don't need to worry because lots of the coming seminars are going to go into much more detail. For example, Lee Howe's next week will be talking about the GPU architecture in detail and how it relates to compute, and the following ones from there will have deep dives into different aspects of OpenCL, and I will return later in the series. Okay, so OpenCL. With OpenCL, you can leverage both CPUs and GPUs to accelerate parallel computations. And you can, in some cases, and in many cases, get dramatic speedups. That's not to say everything will give you a dramatic speedup, and it's often quoted, people like to quote numbers from like 100x to 1000x, and I'm sure that you will get those in some very specific cases, but the reality is we really, you're talking about maybe 10 to 20x for an optimized program if the program suits the programming model, and in particular suits the kind of data parallel execution that I'll talk about in a bit. So, I mean, I don't think 10x is anything to laugh about. That is a good speed up. So even if you don't get the 100x that some people like to tout, it's still, you can expect good speed ups if your program has lots of parallelism. And you can write portable code across different devices and architectures. And in particular, at the source level, you can take a language, an OpenCL program that was written for AMD's GPUs. You should be able to run it fairly simply without modification on NVIDIA's GPUs. You may have slightly different performance characteristics because of the memory hierarchy and those sorts of things, and you'll hear all about those in future talks. But overall, the code should pretty much run on different places. For example, it might well run on in IBM Cell and things like that. And with AMD's implementation, we provide both a CPU and a GPU implementation of OpenCL. So what I mean by that is that the CPU devices are exposed as compute devices and can accelerate parallel computations as well. And that's not necessarily true in some of the other competitors' implementations. And we've had a release for approximately a year now. It's just coming up to December 2009 was when we released both the CPU and the GPU implementations of OpenCL, and we're up to 2.2 now, and in the near future we'll have 2.3 as our releases. So just to give you a high-level kind of overview of heterogeneous computing, what would your application look like if you're using OpenCL? Well, that's most likely going to be this kind of brownish kind of gray box that sits at the top. And then coming down, you're going to have the obvious libraries, the middleware libraries, the video, the imaging, the math libraries. You might have some high-level frameworks, an object-oriented framework or something like that. And then you're going to have some tools, compilers, and debuggers all going down into these different layers. And at the bottom layer here, I've got OpenCL and Direct Compute, because if you're on Windows, Direct Compute is definitely a choice, an option. to use. And underneath that, of course, is all the hardware and everything. And so OpenCL is quite low level, and it's probably not for everyone, and it's quite verbose in places. But if you're willing to put in the effort and your application has the right characteristics, then you can expect to see very good reward in terms of performance. Okay, so today I'm going to talk about what is OpenCL. It can be broken down into what's called the OpenCL platform, which is kind of basically the host API and its model of connected devices, e.g. the GPU. Its execution characteristics, and also I'll touch briefly on its memory model. And again, particularly the execution and the memory model, over the next few seminars we'll go into deeper discussions about these things and their impact on designing OpenCL applications. I'll talk about the OpenCL framework, what you need to do to set it up and allocate. Resource allocation means things like allocate memory and things like that on the devices. And you need to build up and compile your kernels, which are the unit of execution that will run on these devices. These kernels are expressed in a language called OpenCL C, which I'll talk about, and I'll give an example. And then at the end, I won't answer any questions during, but please feel free to submit them. At the end, I will try and answer as many questions as time allows. Okay, so what is OpenCL? So OpenCL is a platform-based model, and this is at the highest level. You have a host, which you can think of as a conventional CPU is the most likely thing in a desktop, with a number of devices, which could be the host itself, connected via some bus. So if it's another CPU or the CPU itself, then it'll be connected via the hypertransport. Or if it's a GPU, then it's most likely today to be connected via a PCIe Express. And over time, us and Intel and others are kind of removing the PCIe bus and replacing that with maybe hypertransport or some other bus that sits in the middle there. And a device itself, from an OpenCL perspective, is seen as a collection of compute units. You can see in this diagram here we have a number of compute units going from front to back. And the compute unit itself is broken into a number of processing elements which execute in SIMD, so SIMD, a single instruction, multiple data execution, or a single program, multiple data execution. And so each of these little blue vertical rectangles will be executing in lockstep down on the compute unit, your program. So they will be executing in parallel, all the compute units completely execute in parallel, and the blue units execute many instructions at the same time. They execute one instruction but multiple times on different data, potentially. And so the execution model itself is based on a notion of a kernel. As I said, this is kind of basically the unit of executable code. It's very similar to a C function, and it's what you will call from your host side application. You'll do what's called a dispatch, and to execute this code on the device. And so basically it exposes an entry point that can be called from the host. And so you can see it very similar to a dynamic library in some ways when you collect them together into what's called a program. And a program is a collection of kernels and other functions. So kernels have this property that they can be externally visible and externally called from the host, while functions can be called from kernels and other functions, but are not externally exposed to the host program. So you can see them as kind of analogous to static functions in C, for example, if you're familiar with that. And then one of the main kind of contributions, I would say, of OpenCL, one of the things that differentiates it from CUDA, for example, which is quite similar in many ways to OpenCL, is that we have this notion of queues where you can in-queue work on the host. So you can create a queue, and then you can say, perform this read operation or perform this write operation, or in-queue a dispatch, a kernel for execution. And these things can all happen asynchronously, so you can build up queues of work. And these queues can be in order, and so i.e. if you submit kernel A for execution and then you read back the data from that as the next command, then the kernel will have completed before the read begins, so you don't have to worry about the dependencies. But they can also execute in out of order execution, and if they're happening in out of order, then of course things might creep ahead, so the read might creep ahead of the kernel execution, which could give you the wrong behavior, unexpected behavior. So there you would introduce an event, which I'll come to later on, to enforce a dependency. Okay, so there are two kind of main execution models in OpenCL, data parallelism and task parallelism. The most kind of prominent one today, certainly the most efficient for execution on the GPU-style devices, not necessarily on the CPU devices, is the data parallel model. And the data parallel model, you've basically got an n-dimensional computation domain. So what I mean by that is you have if you can picture a grid in your head, which could be one-dimensional, so it'll just be like an array of independent elements that are executed on. So you can think of that as a sequential loop, for example, very analogous to that. And then you could also have it in the 2 or 3 dimensions, so you can now start thinking of that as nested iteration domain, so nested loops. For the 2D one, you can have a one that iterates through the X and one that iterates through a Y, say, for example, in the image. And that should hopefully become more explicit in the example below. So each individual element in this domain we call a work item, and these can all execute in parallel, potentially. And that would obviously depend on how many SIMD units you have, and those things, depending how many work items you create. But take this example at the bottom, where we're going to work on a 1K by 1K image, and which is our global problem dimension. So this overall 1024 by 1024 is the number of actual work items, the total number of work items that we're going to execute potentially in parallel. And you can see that's a very large number there on the right-hand side. And so we're going to have one instance of our kernel stamped out for each pixel. So each of these 1024 by 1024. And you can see this if you look at the left-hand side for the scalar multiplier example here. It takes two inputs of 2 float buffers, inputs A and B, and writes the result of multiplying those 2 inputs out into the result. We pass in n, because n is the amount of arguments that we're going to process in this thing, and then we do a simple loop where we iterate it through. And I'm sure that everyone should be familiar with this kind of standard iterative approach on the CPU, for example, to multiply 2 buffers and store their result out to each element of the buffers. And in the data parallel world, so in the OpenCL world, we go to the right-hand side, you can see that we've introduced this keyword now called kernel. So kernel is just a keyword to mark to say this is an entry point from the host, a potential entry point. And you can see that if we don't worry about these attributes that say global here, these are called address qualifiers, we'll come back to those in a minute, we can see that we've got our normal A and B inputs and our result output, but the loop's gone. We've completely flattened the loop, because now the loop is implicit. And what we do instead, because obviously we still need to get the value for I, or in this case ID, we can use the get global identifier routine and use that to index into our A and B. So get global ID will return exactly the same values for I across the whole iteration, assuming that we've launched our global work size to be the same as n. And we'll come more to that in a minute. Okay, so as I say, we're basically going to express data parallelism in OpenCL by stamping out these kernels, executing them across a global domain of work items. So that was our total work items, our 1024 by 1024, for example. And this is what we call global dimensions, and they define the range of the computation. And one element within that is called a work item. And work items can be grouped into local. And what I mean by that is that these global work items are completely independent. There's no way of doing communication. Actually, we do have atomic operations, but generally there's no way of doing very fast communication between collections of work items until you group them into work items. Now, work groups have a local dimension, so you could have you could have a 2 by 2. Or let's say we had a global size of 4 work items, and then we wanted a work group of size 2, then you can see that we could have 2 work groups executing, because they'd each take 2 work items and group them into a work group. Now, the key point about those work groups is that they get executed on one of the SIMD cores. And so if you had a giant work group that had all of the global work items, and you had 20 SIMD units, you'd actually only be using one of them. So you wouldn't be fully utilizing the device by any means. There's lots of other reasons why you might not be fully utilizing it, but that's just one of them. And then you can see that they are, the key thing about them, though, is that they can share local memory and they can synchronize between each other. Now, this local memory is similar to a cache. It's called a scratch pad. It's managed by the user, but it's very, very low latency. So, for example, a load or a store on AMD architecture can take 4 cycles, assuming there's no conflicts with memory accesses. But if you're independently accessing memory locations in local memory, then it's very, very fast, certainly compared to the hundreds of cycles that it can potentially take to go out to global memory. And synchronization allows you to say that I'm going to write to this memory location, wait until that memory that memory operation is completed, and then another thread running locally, another work item, can then read back that from that memory location and know that it will get the value that was written by the other work item. So now you're starting to share information and communicate between work items in a work group. And the key thing is that synchronization can only be done within a work group. Okay, and you can see this in a little bit more of this problem here. We can start to build it up. We have a single work item, and we have another work item, and then multiple rows of work items. And then you can see that we have this whole grid of execution. In this case, it's a 2D grid, 1024 by 1024. And you can see that if we put a work group, we group them into these two work items within this box here. You can see that we can perform synchronization and communication. However, if we have 2 individual work groups, because these are actually work groups, then you can see that these 2 work items cannot communicate via each other. There are atomics to global memory, so they can do some kind of communications, but the latency, again, is much bigger than it would be by doing the communication within the work group. Okay, so I talked a lot about data parallelism, and that's mostly what we'll focus on with OpenCL over the coming talks and weeks ahead. However, it does support task parallelism, so you can execute the kernel with just a single word item, and so there's no iteration space, or the iteration is just one. And the nice things about this, so that if you're running this on the CPU device or the host device, you can actually pass in natively compiled code. So one of the advantages here would be that you could start to build up using the OpenCL queuing model and synchronization features of the host API, and benefit from that and integrate that into your program while still running, standard C and C++, calling I/O functions and so on. Or maybe you've got some C library or C++ library on the host that you don't have the source to, so you can't port that, to the OpenCL, for example. Okay, so now I talked about, I kind of glossed over back in our example when we did the vector multiply, I glossed over the fact that I had these address qualifiers, I called them, when we said global. Now, OpenCL differs from C in this case, that it explicitly exposes the memory hierarchy of, particularly of the GPUs. And you can expect this to be the CPUs as well. And in particular, it says that the host memory, which is this red box down here, is a distinct memory. The orange memory here is a global memory, which is distinct memory again. And then within inside, and you can see the global memory, of course, is visible from any work group, but it is not. Other than using atomics, you don't get any consistency guarantees or anything like that, and you can't do barrier or synchronization operations, so you can't induce those consistency guarantees either. Now, inside the work group, we have this green box. This is the shared memory that I talked about, the local memory we call it, and the work items can all get access to this local memory. And because we have the barrier operations and the synchronization, we can, the programmer can induce an ordering, so they can get consistency. They can get one work item to write a value and then do a synchronization, and then you can have another work item read that value back, and you'll get that result. You won't get some undefined answer. And then each work item also has its own private memory, which is completely confined and defined within the work item itself. And so this is the memory hierarchy. Now, it has its advantages. It's very powerful. You can really get a lot of performance from it. And programming for to the size of your caches on the CPU and knowing about those things can really improve performance too. The biggest issue is that whilst the CPU will often help you with implicit caching and those sorts of things, is that all the memory management has to be explicit in OpenCL. So moving from host to global and global to local and all the way back again, all has to be done by explicit operations, either by host calls to transfer the data onto the compute device or by doing loads from global memory into local memory and then back again and so forth. So that could be slightly complicated and requires some thinking about of your algorithm. The compilation model is based around OpenCL, and so it has an online compilation model where you can pass in streams or strings of OpenCL-C source programs, and I'll come to OpenCL-C in a minute. And you can compile this and online, and then you can build up and you can extract kernels from it and you can dispatch to it and execute them. It is possible to OpenCL provides an API for querying from a compiled program to extract the binary, and then you can then serialize that binary to disk and then read it back at some later date. Now, the advantage of that would be, one, that you avoid compilation time penalties at startup of your application, for example. And the other key, probably more important factor is that it allows you to hide your IP, so that there's no need to distribute the source within your program. And of course you could encrypt your source and everything, but it's always possible to have things. If you don't transmit your source, then there's never going to be an IP issue around that. And AMD, and as I believe some other vendors do, also support different types of binaries that you can save, anything from a simple text style representation to a full ISA representation. Okay, so using the OpenCL framework. So OpenCL is it's really built around this notion of a context. A context is a OpenCL object that allows you to associate devices with it. It allows you to associate memory objects, and I'll talk about those in a bit more. And it also defines a memory consistency model between those memory objects. For example, you allocate a memory object against a context, and so even if you generate data on the GPU into that memory object, once at some point after that event is guaranteed to be complete, and I'll talk about events a bit later, then you'll know that that memory is consistent and consistently visible from the CPU in this context, if you have two associated. If we had two contexts and the GPU was in one context and the CPU was in the other context, then there is no guarantees across contexts. It's just within a context. And you can see that we've associated queues here, each with one and with the context, but there's also bound to a device. So a queue, is associated not only with a context, but it's also associated with a queue. You can see it as the kind of execution engine for a device given a particular context. And generally what you'll do is you'll probably query the system to, the OpenCL API allows you to query, and I'll show you some examples of that in a minute, to query what devices you have in the system. For example, you can select all the devices, or you can query, can I get the GPU? Do you have a GPU, or do you have a GPU with these capabilities? Do you have the cell broadband is not a separate type, it's actually an accelerator type. You can say, do you have any accelerators? Do they have these capabilities? So there's lots of different things you can query about the devices. These are statically known, of course, to the OpenCL runtime as it starts up, and so the topology, it configures the topology as it goes on. And then you get to context, which I told you are a collection of devices and also a collection of memory objects, which I'll talk about in a minute. And queues. Queues are the place where you submit work to a particular device associated with the context. Now, memory are buffers. So buffers are one-dimensional blocks of memory. You can think of them as arrays, and they're allocated as opaque types on the host and appear in the OpenCL C program or the kernel as a pointer to a memory region. And because these things, a lot of this stuff was based on work from GPUs, there is also an opaque type of notion of images, because it turns out that GPUs have a lot of hardware built to optimize the access of images, so that, for example, certain data formats, and you can do these things called samplers, which allows you to set up how you read edges of images and things like that, whether you want to set them to 0 when you're out of bounds and things like that. There's lots of different types. And images are strange because they're not that common to people who don't work in the graphics. So when I first came to it, I was a little surprised, what are these image objects? But they can turn out to be useful, certainly if you're doing imaging style applications. And then, of course, the other thing that you'll do have OpenCL objects for, and you want to manipulate on the host side, is you want to be able to build up programs and compile them, extract kernels from them. For kernels, you're going to want to be able to set their arguments, and of course, you're going to want to be able to execute them by enqueuing them onto these queues. And finally, I've talked quite a lot about that, and I'll come back to that in a little bit, is that almost all of the enqueue commands in OpenCL are asynchronous. And so, of course, if anything's happening, if you want to build up dependencies between these things, there needs to be some way of doing that. So it needs to be, say, you cannot execute this command until this one is completed, for example, and that's what OpenCL events are for. Events allow you can query them to see what status the command is, but you can also pass them into enqueue commands and say, don't do anything until this event or this set of events has reached a certain status. I'll talk about that a bit in a minute. So you can see the overall framework here for OpenCL. You've kind of, you're compiling your code, building your programs. You can see that from a single source, we've built up a CPU binary and a GPU binary. And you can extract kernels from here. You see we've got the add, the kernel objects. You want to be able to set their arguments. We have memory objects, images, and buffers that we talked about. And, of course, we have these command queues. And here you can see that we've created a command queue for the GPU. You can have multiple command queues pointing to the same device. And so even if your queues are both in order, if your operations that you're submitting down one queue are dependent on operations that you've submitted down another queue, these queues run asynchronously. Even if they're in order, you're still going to need to build up dependencies between them to guarantee the correct execution. It may work, but it's undefined whether it would or not. So you need to make sure that you use those things carefully. Okay. So here's kind of getting into a little bit of code here. You can see that for the setup that we talked about, you can use CL get device IDs to query GPU device or query the device ID for CPU devices. Now, if you have multiple CPUs in there, we actually expose an aggregate device, which means that even though you might have an 8-core CPU machine, we actually will expose that as one OpenCL device. But if you had multiple GPUs in here, then because we're just passed in one as the third parameter to get CL devices IDs, then we're just going to pick up the first GPU. Most likely, I think that's what our implementation does. Of course, it could pick any one, but obviously the easiest thing is if you knew that there was 2 GPUs in there, and you can do that by using this same function just to query the number of devices returned without actually passing in a place to store it. So this devices could just be null here. And then you get back just a number of GPU devices. And then, of course, you could then allocate some memory for devices and then pass in that total number if you wanted to get back all of them. So that's very common in OpenCL because it's a C API and it doesn't want to do any memory allocation for you because of all the issues of kind of space leaks and so forth. What it does is that it allows you to query how much, what size it's going to return. You can then allocate some memory and then get those values back. And so this is device IDs, as I said, are kind of static in the sense of that, the OpenCL runtime at start time knows exactly how many they are. You can't just come and stick in another device. It's not a hot swapping thing. Once it's determined how many devices are in the system, it will get that. So get device IDs returns a static number. It will always return the same number of GPUs if you ask it for how many it has installed and CPUs and so on. And so in that case, when we're not actually returning a newly created object, an OpenCL object, we will always see that these commands will return the error code here at the end. And you can see that in the case when we get down to the CL create context here, you can see that we're actually going to be passing in our list of devices. We're saying that we have 2 devices. Please create that. You can see that we're not actually returning an error code. We're actually returning the CL context object type. Now, this is the 2 distinct APIs types in signatures in OpenCL. If it's not returning a CL object, it will return the error code as its result. If it's returning a CL object, it will return that as its result. And the last parameter here, you can see the ampersand at the end of CL create context, will be where the error code is returned. Every function returns an error code. And you can see that, again, we can see this with the CL create command queue. You can see that this takes a context, takes an individual device now, and not just a set of devices. It takes one particular device, because queues are associated with a device. And you can see that these, of course, are returning an OpenCL object, the queue. So this gets returned as the return value of the function. Okay, so I've kind of described that. So devices, there are multiple cores of CPU and GPU together as a single device, and so I told you about the CPU. We expose that as an aggregate device. If you have a 4-core CPU, we'll give you one OpenCL device. There is an OpenCL extension that I'll talk about later in this series called Device Fission, which allows you to subdivide one of these devices and talk about cache affinity, for example, and get back multiple devices from that. And that's very useful. And today we support that on the CPU, and you can potentially expect that maybe in the future that might be something we'll be looking at for the GPUs too. And obviously we have a number of assembly units and compute units that are on the GPU. I think on our 68,000 series that we've just launched, I think the high-end part there has 20 cores. And OpenCL executes kernels across all these cores in a data parallel manner, which is kind of what we talked about. It does do the task one as well, but particularly the data parallel is the thing to focus on here. Context. Now, I talked about that memory is allocated at the context level, the buffers and images. And so these are shared across devices. And once you know that certain events have completed, so for example, if you enqueue a write to a particular buffer on a particular device, once that event has completed, you know that it will also be visible on any other devices that are available in the system. And there are lots of kind of these get info functions. So if you see here, down here, you can query a device info. It's CL get device info. There's actually many OpenCL functions called CL get X info, so for X being device or context, or where you can query information about CL objects. Now, I put the device one in because that's probably the one that has the most. I think it has maybe 100 different queries, and it's probably one of the most useful ones in the sense that it's something where you can really ask a device what are its capabilities. For example, what's its maximum number of compute units? What's its clock frequency, for example? What's its global memory size? Does it support certain extensions? Double precision, for example, is an extension. In 1.0, atomics were an extension, and 64-bit atomics are still an extension. And so you can query these capabilities to determine what device. So maybe you have multiple GPUs. Maybe one of them doesn't have atomics and one of them does. Maybe you want to use atomics, so you just use the one that has it. So you can query these capabilities. And that's one of the things. It's quite painful the first few times when you set this up in your program. But once you have a little routine, or maybe a library routine that can query this and get back the information that you're interested in, then it becomes very useful. And as I say, pick the best device for your algorithm. And so buffers are simple chunks of memory. They are, kernel can access them however they like. They can be arrays or pointers or structs, so you can store user types in their structs or unions. And kernel can read and write them. You can do full scatter-gather on those. Images, on the other hand, are opaque special types represented in hardware on the GPU. And within the kernel, for that restriction, you can only access them via these read image and write image accessors functions. And it turns out actually you can only read an image or write an image in a kernel. You can write to one image and read from another image, that's fine, but what you can't do is read image A, write image A in the same kernel. And again, that's to do with the way that addresses and everything are pre-calculated for images. I'm not going to go into details about images, but you can have a look about the slides when they get posted on the OpenCL zone in the next few days, and you'll be able to see that there's lots of things around formats and all this kind of things. And as I say, the benefit of images is that we have special hardware, particularly on GPUs, to accelerate their access. And here's some more code on how to allocate buffers and images. You can see that we have, again, when we do a CL create image or a CL create buffer, as we do here, we get back a OpenCL object, so it's as a return value, because of course we're creating a new object. You can see these pink enumeration values here allow you to describe how you're going to access these buffers or images from within the kernel that will end up using them as either input or output. So you can say a read-only for an input, so it knows, so the OpenCL runtime could then cache that, always would never have to make that back to the host, would never need to do any consistency, so it may have special ways of putting that in the right places. And of course, if you do want to read it back, then you might get the wrong error because that's not what you said you're going to do to it. You know, for example, if you want to write to a read-only buffer in a kernel and we've stored it in constant memory, you know, you might get an exception, for example. Reading and writing memory objects. How do we write those? So these are our explicit commands to access memory object data. So this is what I go back to my original diagram on my memory hierarchy where I talked about everything is explicitly managed in OpenCL. And so this does make a bit of a burden on the programmer, but obviously you can control your data placement and data move. And so you can, this is the first time we've seen an enqueue command. So an enqueue command is how you enqueue commands to a queue. And you can see this is a CL enqueue read buffer. And here we've passed in a queue, we pass in an object, which is the buffer object. We've got this blocking parameter, which I'll talk about in a minute. You can have an offset, the size of data that you're writing, the host pointer that you're going to copy the data from, and this will get transferred to the device associated with this queue and this object. And of course, because it's against the context, it will become visible to everyone in a bit. And this ... is how we make that visibility, and I'll talk about that in a little bit. And of course, you can do the opposite. You can write to a buffer. Sorry, that was the read, and this is the write. And then you can map a region. So what you can do is you can actually get a host pointer. It will put it in pinned memory, for example. You can then iterate through with a for loop and then write to that buffer. Now, there are some advantages of doing that, and that you'll need to look at your vendor's specifics around that. We have some advantages of doing that for small regions, but of course you won't be using the DMA units in general then. Whereas with the read and write buffers, it's quite potential that you'll be using the asynchronous DMA transfers. And you can copy data as well. And so there you can copy from buffer to buffer. Now, of course, if the data is just on one device, then it may not need to come back to the host at all. It can use the data transfers on the device itself. So there may be some benefits there. And in general, all enqueue commands are asynchronous. So that means they'll return before the command is completed, potentially. And except in the case of these read and writes, where you can pass in a blocking parameter. So this is the one up here on these two wings that says blocking. And if it's set to CL true, then it will operate synchronously. Otherwise, if it's set to CL false or anything else, it will execute asynchronously. Okay, so as I said, program objects encapsulate sources or binaries, and contain a list of kernels. You can query them to find out the list of kernels. If you know the kernels, you can do that. Kernel objects encapsulate a kernel function in the program, and you can set argument values for them, and you can use different ones. And here you can see that we can compile the same program to the x86 or the GPU. And here you can see at the top here we're going to be able to set some kernel arguments, everything like because it's a C, we start at kernel argument 0, we use the 0 index, and then 1 for the second argument. Set kernel arg takes a kernel, it takes the size of the input that you're setting, and then a pointer to the values that you want to set. We're going to set up our global dimensions here, so this is our image width and image height from our previous example. So it's the 2D, we put 0 in the third dimension because we're not going to do anything. And then we see an ND range kernel, so this is executing the dispatch that we talked about right back at the beginning, the domain or the grid of execution that we're going to perform. Of course, we're going to run this on a queue because it's going to get dispatched onto a particular device. We're going to pass in a kernel because we want to run a particular kernel. And, of course, we pass in our global dimensions. And then... Okay, so here we have... I had these ... at the end of that, and here is where we can start talking about events. A command queue has some notion of dependencies can be built up on here, and in particular you can see that if we have this Q1 and Q2 here, even though they're in order, because these events C2 and C1 in Q2 depends on the event, the command C3, we need to set up some dependencies, and we need a way of doing that. And obviously, in this red one, which is an out-of-order queue, we may need to set up dependencies within the queue itself to guarantee that things don't overtake each other. And so this brings me to the ... arguments, and I put the ... at the front for the enqueue commands. But every enqueue command takes 3 arguments at the end of the function. Here is the number of events in a wait list and a wait list. So these 2 things correspond to the events that you can pass into the enqueue command to say, do not execute this command until all of the events in this wait list are completed. And then the final argument is appointed to the event that you'll get back out associated with this queue, which you could then pass into other ones, or you can use it to query information about it. So, for example, you could use CL wait for events to wait for all events to complete, and that will block the host thread at that point. You can enqueue a marker into a queue within a particular event, and you can enqueue a wait for events too, so it'll run asynchronously and you'll get back an event associated with that. And you can actually query using the get info functions again, but this one for an event, you can query the type of status of the command. You can see there's 4 different states that it can be in. And finally, you can actually query if the queue was created correctly with profiling information enabled. You can query different times for each of these 4 different states that you have. So you can start to do naive, reasonably naive, but 64-bit accuracy pointers. Okay, so the final part of the talk is going to be about the OpenCL C language. Again, there's a lot of detail in OpenCL C, and you're going to be able to get lots of that. There's going to be the seminar after next is going to go into a deep dive into OpenCL C language with a much further developed example. And here, I'm just going to say that it's based on C99. It has some restrictions. For example, recursion is not allowed. It has some additions for working with parallelism. So we talked about work items, work groups. It has these vector types, which I'll give you a little example in a minute, and it has some synchronization primitives, so the barriers and things like that. It has address space qualifiers that we talked about, local, global, private, and it also has constant. It has images, and it has a vast amount of built-in functions that you'll need to look into the spec. There is a large number of those. But anything ranging from sine to gamma to things on vectors and some simple matrices. Operations. And you can see that an example of one of these built-in operations, which is to do with work items, is the get global ID, which will give you the independent index in the launch domain, the global index into your thing. So here you can see that we're getting the 11th here and reading the value and the output. And there's lots of different ones. So if you're working in a work group, you can do get my group ID, and then you can get my the local size, which is the size of the group, and of course you can then calculate the get global size, for example, and the global ID by doing different calculations. So there's different ways to get to the same results, and obviously you use get local ID, which is your local 0 to n of the work group size will give you an index inside the work group, so you can do local indexing independent of the global size. You have all the expected scalar data types, nothing surprising there, and there's the image types that you'd expect, and then there's also the vector types, and so vector types are all the scalar types, but they can be of size 2, 4, 8, or 16. All of the operations on vectors are lifted to that space, and then we have a nice algebra for constructing and deconstructing vectors too. And there's lots of different operations. This just gives you an example. And as I say, there'll be lots more of this in the coming talks. And address spaces, kernel arguments can be global, local. Local is the shared memory on the compute unit itself. The global is the buffers that get stored into global memory. You can have things that are private as well. Of course, they can't be passed as arguments to kernels, but they can be passed as arguments to functions, and they can be private values can be stored, allocated inside of the kernel itself for a function. And here you can see that there are also constants. Constants are special address space that just appears at the global level, and so forth. And as I say, there is lots more about OpenCL C in particular, and I just wanted to give you a kind of brief flavor, kind of touch on what that is, because that's a seminar in itself, and it will be. We're going to go into a lot more detail about that, and so don't fear that I've kind of gone over it very quickly and worrying. But what we do have now is that we have enough information, we've covered enough, even though very quickly, to go for an example. And this is going to be the end of my talk now. And so this is going back to a very similar one that we had at the beginning of the talk, but I've done a vector add here rather than a vector mul. And you can see that we've got our inputs and outputs, and we're doing the OD, and we're doing an add, and we're storing the result into C here. So that's our kernel. To our host API, the first thing we do is we can clear a platform, because we could have multiple platforms, which means multiple vendor implementations installed in the same system. Maybe you've got an NVIDIA implementation and an AMD implementation on the same machine, and you can query that. There's a whole platform API for doing that. We can create a context here. We decide, just give me back a context with all possible devices. And I'll do that with a particular platform, so maybe a CPU and a GPU if you're using our platform. You can query the context to get back the set of devices. We first query to find out how many we got, and then we get the actual set of devices returned. Because we'll need that, remember, to create our command queues. We just pick the first device just for simplicity in this example. And then we're going to create our memory objects. Here we can create that against the buffer. As you expect, we create 3 memory objects, 2 for input, 1 for output. Use the enumerations as expected. And we'll build our program. We create a program with source. We use a context because we're going to build it against the devices for that context. We pass in the source file. And so we create the program, and then we build it. And then, of course, we extract the kernel. So this is how we create the kernel object. We pass in the string vector underscore add because we know which kernel we want to do. We set the kernel arguments. There's going to be 3 arguments, so that will be 0 to 2 as expected. And we pass in the size of the CLMem object because we're actually going to pass in a CLMem object as we're doing here. And then finally, we'll just do a single one-dimensional launch. We'll set that to n. N is the number of elements we're going to do for the add, and then we'll simply enqueue that. And as we're going to do the read buffer here, we're going to do a blocking read back. We don't need to worry about events because we know that we have an in-order queue, and that we're going to, the read buffer will not start until the kernel execution is completed. And we know that as we're getting CL true, that the read will not return until it is completed. And so that's the whole program, pretty much. I mean, obviously there's a little bit more that you need to add, header files and those sorts of things. But hopefully that gives you a kind of whistle-stop tour of OpenCL and what it is. Okay, so now I've just about got there, and I'm going to try and answer some questions. I've got lots of questions, so I'll go through as many as I can given the 10 or 12 minutes that we have left. So one of the questions is, how is data parallelism different from compiler performing loop unrolling? Now, in fact, it's not. So loop unrolling, well, not loop unrolling, but loop tiling. So you might want to do some loop unrolling because, if you just unroll a loop, then you'll still just execute that sequentially. If you can discover that there are that the actual iterations of the loop are independent, or at least some number of those iterations are independent, then it's feasible that you could execute those in parallel, and that would be a data parallel execution. Absolutely. One of the big problems is, of course, that compilers aren't that good at doing that. They struggle to do that for, ICC, which is Intel's C compiler. It does a reasonably good job for quite a basic loops, and that's on a SSE 4-wide machine. We're 64-wide SIMD, plus you can run 10,000 of those threads, and so imagine trying to vectorize for that. That's quite a difficult task, and it's possible for some programs, but it's not possible for many, and without doing a lot of restructuring, and it's very difficult then to do memory optimizations and memory parallelization as well. So in the end, I think you do need to explicitly parallelize your program. Even if it's not for OpenCL, you'll need to explicitly parallelize it for some other model. That's my genuine belief going forward. So I have a question. CL NQ marker would only be useful in an in-order queue, presuming it signals the event, or are events handled especially always only signaled when they're placed in the queue it actually reached. So an NQ marker allows you to say that in an out-of-order queue that you could stick in a marker into the queue after you've submitted ABC, and then you could submit XYZ, let's say, and then those commands XYZ could mix up in the order of those execution, but they could never go before ABC is completed. So what it allows you to say is that nothing can go past this point. Anything I submit behind that will not get executed. So it's useful for out of order queues as well. When you refer to constant memory, that's not to say that the values are constant, is it? It seems like the word constant global were almost used interchangeably. No, actually, it does mean that the values are constant. So I'm sorry if I was not clear about that. They are a globally visible memory. So they are at the same level. All work items can see it, but you cannot write to constant memory. And we actually have special memory, particularly on our GPUs, where we will load it up into very fast constant memory, because we know you're never going to write to it. We can put it in a special place where it can get very nice cache capabilities and so forth. And on the debugging side, on the CPU side, we mark constant. We put them in a special page if you're debugging, and we'll mark that page as read only. And so you get an exception if you did it right, just so that you can actually track your program, debug your program a bit. So I got one question. Missed the whole thing. Unexpected airport pickup. Can you suggest an online web resource I can use to catch up? So we are going to post all of the seminar series on AMD's OpenCL Zone, and there's lots more information about OpenCL, and obviously the OpenCL Zone. There's lots more information on the AMD website. Generally, you'll find lots of information about parallel programming and other programming models such as tasking and things like that. But the OpenCL Zone is a great place to start resourcing it and finding out about OpenCL. There are lots of other good websites too, but I would say recommend looking there. So get global ID 0 returns the same value for every call of the kernel. I'm not quite sure I understand that question. So if I understand you rightly, so when you launch a kernel for n work items, you'll get back 0 to n-1 values for each of the work items that call get global ID 0. The next time you call that kernel, if you launch it again for n work items, you'll get back exactly the same value. 0 to n minus 1. So basically, it's the same as in your loop. If you're doing, in our original loop that we had at the beginning, I equals 0 to I less than n, I plus plus, you'll always get the values 0 to n minus 1. So it's exactly the same. Really, all it's doing is saying it's a way of getting back that value for I in the loop, because the loop's gone now. So we need to have some sort of built-in operation for getting that back. We've made the loop implicit rather than explicit. So what happens when two different applications are both running and both trying to use OpenCL simultaneously on the same machine? Do they share the hardware, or is one application locked out? Well, I suppose that will depend on the vendor, but as far as I know, all implementations today will share the hardware. And, that's the OS will kind of multiplex the applications. When you submit a kernel, because the GPUs today are not preemptive, then that kernel will run to execution and it will come back. And then if your time slot is up, the OS will swap you out and maybe run the other application, and it can submit some kernels and so on. And so no one's locked out, and so forth. Obviously, if you run a very big, very long kernel, then bad things might happen. So which profiler would you recommend OpenCL? For OpenCL? So compute visual profiler. So we have a visual profiler which allows you to query lots of information about AMD hardware. You can query, the AMD GPUs. You can do that, and I'm sure NVIDIA have. Actually, I know NVIDIA have a very similar product which you could use too if you're working on their hardware. So both of those things are good solutions, and I think they're good, but they're maybe not the familiar. They're not, you're not doing. They're not the kind of profilers where you're kind of profiling how many times you hit a loop, for example, and stuff. What they're really looking at is how many ALU operations you've entered, how many cache misses you did, and so forth. We have two versions of it. We have one that is a plug-in to Visual Studio, which if you're using Visual Studio on Windows development, then that would be a good one to use. If you're using Linux, for example, then we have a command line version that you can run, and then you can get back a spreadsheet to view the different operations. So, the Visual Studio one is basically the same. We just have a little GUI front end for it. And in the near future, we'll be having an integrated environment for all of those things on both platforms. Okay, so how large is the overhead of loading the data into the image object or buffer? Now, so I'm assuming you mean that by kind of transferring it. I mean, that would depend on the device and how you set it up. So, for example, you could allocate it as a host buffer, use host memory, and then on the CPU, the cost would be very small. It would just be a simple data transfer. You'd be running out the bandwidth of the CPU, so it'd be like doing a copy memory, for example. Now, if you're transferring across the PCIe bus, then the overhead is the startup of setting up the PCIe bus, and then of course the max you're going to get is the bandwidth for the PCI, which is 16 gigabits, and approximately at least, I think. And obviously it is dual channel, so you might be able to overlap some of those things. And we have DMA engines and everything that will kick in those things, so you could be doing things asynchronously. But of course the latency of the PCI is still reasonably high. So you want to be transferring large amounts of data. You're probably going to want to be double buffering if you have got a lot of data that you want to work on. So say for you've got a video stream that's coming in, you're probably going to want to be doing, maybe 5 frames and another 5 frames, depending, how you do that to kind of batch it up. I know that's some work. I've been working with someone who's been doing it like that. They've been doing some video editing software. Okay. I'll take one more question. So what changes to OpenCL best programming practices are expected considering recent introduction new AMD 6800 GPU series, if any? So actually there aren't any. So that the 68 series that we've launched so far are all based on our Evergreen architecture, which was the same as 5800 68,000 series. They have some innovations. There's some more SIMDs, and the memory is slightly different, but the actual characteristics of the GPUs themselves and the way that they're designed, they're a 5-way VLIW, well, it's a 4-way VLIW for 68 series, and no, that's not true. That's 5-way VLIW, and things like that are, because they're based on the Evergreen architecture, they're pretty similar. So if you have the best practices and you're already doing that, your code is optimized for Evergreen, you can pretty much expect that you'll see a benefit from the 68,000. And the parts that we've launched so far are these are really targeted at the middle to low end market, and there you'll get some real benefits both in cost and in performance from the same application, at least in theory. Okay, well, we're dead on 8 o'clock, and so I'd like to say thank you very much for joining us. And